Welcome to the full solution to the practice questions from the vector lesson on forces. In the first question, we're asked to determine the resultant force for part A, force of 70 newtons northwest and 50 newtons in the south direction. So the first thing we want to do with this is to draw out all the forces to kind of give us a visual of what is happening. So the 70 Newton is in direction northwest, and I'm going to take my coordinate system to be positive in the directions and north and east. And my vector here is going to be in the northwest direction, and that's the angle right in between here. So I'm going to say 45 degrees here and 45 degrees here. And it doesn't really matter how you label this, but I am going to label this side as the x component. So this is going to be the adjacent side to 45. So this is going to be 70 cosine of 45 because it's adjacent. And this component here is going to be opposite to the 45 angle. So it's going to be 70 times sine of 45. The second one, or the second force here, is acting downwards. So we don't actually need an east and west direction for this one. This one, let's say if this was our origin, it's just going downwards at a magnitude of 50 newtons. Let's call the first force force 1 and the second one force 2. And basically we have to add them up. The resultant force is the addition of the two forces. So F, I'm going to call it F net here. The resultant force is going to equal to F1 plus F2. The x component of F1, we are taking east to be positive, and this is going in the opposite direction, in the west direction, so I'm going to use negative 70 cosine of 45. And force 2 here doesn't have an x direction, so this is going to be plus 0. For force 2, we are taking, for the north and south direction, or in the vertical direction, I'm taking north to be positive, and 70 sine 45 is going in the same direction, so I'm going to use a positive value here, 70 sine 45 from force 1. And for force 2, it's 50 Newton. It's going in the opposite direction as what I have chosen as my positive, and therefore I'm going to use a negative value here, so negative 50. Using my calculator, when I plug in the x components, I am going to get negative 49.4975, and for the y components, I'm going to get negative 0.5025, and the numbers continue. I'm just going to leave them in 4 decimal places for now. In physics, when we want to figure out the final solution for a net force, we usually want the magnitude and the direction. This is nice. This gives us the component form of the vector. But what we want is the magnitude and direction, or an angle. So I'm going to draw the x component. The x component is going in the west, and it has a magnitude of approximately 49.5. And it's got a y component of negative 0.5. So the negative, what I'm doing here is I've taken right to be my positive, so negative here means it's going to the left, and I've taken up to be my positive, so negative means in the downward direction, or in the south direction. So it's going to be a very small value, and it's going to be 0.50 approximately. And my final vector is going to originate from here and terminate at the very end here, and I'm going to use this as my angle, and my angle is going to be relative to the west direction and the south direction. To find the magnitude of my force, I'm going to call this F net. The magnitude is going to be the square root of the x component squared here plus x component squared plus the y component squared. So it's going to be negative 49.5, and I use the exact value on my calculator, but I'm just writing it to a few significant figures for just the writing part. So this is going to equal to approximately 49.5 Newton, and this is in three significant figures. Now, this is the magnitude, and now I also need this angle, theta. And for theta, I'm going to use the tan rule, or we know that this is the opposite side, and this is the adjacent side. So it's going to be tan inverse of the opposite, which is 0.5. And again, I use the exact values on my calculator, divided by 49.5, which is the adjacent, approximately 0.582 degrees. So for my very final answer here, F net, or the resultant force, is going to equal to 49.5 newtons. And my direction, first it goes in the west direction and turns towards the south direction. So it's going to be west 0.582 degrees south. That is my final answer. For the next question, we're asked to determine the resultant force for forces of 50 newtons and 40 newtons, which are acting at 160 degrees to each other. Well, one way to see this is to draw the 50 Newton force going in one direction. Let's go in this one. And the 40 Newton is going to be at 160 degrees to it. So we'll draw the 40 going this way. And this angle over here is 160 degrees. Note that this is not the only way that we can draw this out. We could just draw it here, 50 Newton this way, 40 Newton this way, and angle between them is still 160. We can draw the 40 on this side and 50 on this side, or 40 here and 50 on this side. It doesn't really make a huge difference. What does make a difference is our final answer and how we express it. So our final answer is we don't have east, west, south, or north directions here. So we have to give our final answer in terms of what the resultant angle is relative to either the 50 Newton or the 40 Newton, and we'll get there a little bit later. Now, we want the resultant force, so we want to break down the forces into their components and add them up. And I am going to take my positive in this direction, and that's going to be towards the 50 Newton force, and my positive in this direction, the vertical direction, is going to be perpendicular towards the 50 Newton. And you could again do the same thing, choose a coordinate system to be positive like this, or many other ways, but this is one of the most convenient way to do it the way I've drawn it here. Okay, and to clear up things in terms of my coordinate system, our x components are going to be towards the 15 Newton, and our y components are going to be perpendicular to that 15 Newton in the direction of the 40 Newton. Okay, the 50 Newton has only one component and it's going in this direction. I'm going to call that one force 1 and I'll do it in blue. And the resultant force, F net, is going to equal to F1 plus, let's do F2 using pink, and I'm going to label my 40 Newton as F2. Well, F1 only has an x component, and that's 50 newtons. It has no y component, so I'm going to leave that as 0. And I have to add the x and y components of my F2 force. And for F2, I know that this whole angle here is 160. I know that the angle up to this point is 180. So this angle over here is going to be 20 degrees. So I'm going to write that down. So this is going to be 20. And the x component of this force here is going in the opposite direction to my positive. So it's going to be negative. And the magnitude of it is 40. We know that this side is adjacent to my angle 20, so this is going to be cosine of 20. So I'll write this as 40 cosine of 20 degrees. And the y component is going in the same direction as my coordinate system here, and its magnitude we need to find, which is this side is opposite to the 20 degrees, so it's going to be 40 sine 20 degrees. So I'll write that as 40 sine 20 degrees. Adding up my x components, I get approximately 12.4123, and my y components as 13.6808. Okay, so now my x component, I'll draw it out maybe here. My x component is 12.4123. It's positive, so I'm going to go towards the positive direction that I've chosen in my coordinate system. So that's approximately 12.4. And my y component is also positive, so that's going up in this direction as 13.68. And my resultant force originates from the beginning and terminates at the end, and I'm going to draw my angle here as theta. I'll label this as F net, and the magnitude of F net is going to be calculated by Pythagorean theorem, so that's square root of the x component squared, so that's 12.4 squared plus the y component squared, which is 13.7 squared, and I get my final answer as approximately 18.5 Newton in 3 significant figures. And again, when I'm plugging all these values in, I'm not putting 12.4, I'm not even putting 12.4123, I'm putting the number that I got from my calculator, which had about 8 other digits in there. And we want to do that, we want to make sure that we use the most exact and accurate value so that we don't make any errors in our roundings for the final answer. For my angle, I have the opposite to the angle and I have the adjacent to the angle. So I will use theta is equal to tan inverse of my opposite side, which is 13.68, and my adjacent, which is approximately 12.4, and I get my final answer as approximately 47.8 degrees. So my final answer here, I know that my net force is going to equal to it's going to have a magnitude of 18.5 newtons, and its direction is actually, if we look, this direction is same as the direction as our 50 newtons, and the angle is relative to that 50 newtons. So what we are going to write is with angle of 47.8 degrees relative to the 50 Newton force. And it doesn't really make a difference if we were to draw it differently. That angle is always relative to the 50 Newton force. Okay, for our second question, we got a wire which is 50 meters long and it's suspended between two fixed points which are 30 meters apart. A mass of 40 kilogram pulls the wire down at a point, and this was originally 10 meters. I do really apologize. 10 meters will not give us a proper answer for this type of question, so I changed it to 20 meters from one end of the wire, and we want to determine the tension in each part of the wire. Okay, so we're going to draw this out. We got a wire which is 50 meters long. We're going to leave that to the very end, suspended from two fixed points which are 30 meters apart. So let's imagine that this is the ceiling, and within the ceiling there's going to be 2 points, and they're going to be 30 meters apart. So I will draw that here, 30 meters, and I've written all these I've drawn all these information down. We got a mass of 40 kilogram, which pulls the wire down at a point 20 meters from one end. So if it's 20 meters and the total length is 50, that means one of the sides is going to be 20 meters and the other one is going to be 50 minus 20, which is going to be 30 meters. And we're going to have a box attached to it, and this box is going to have a mass of 40 kilograms. So we've taken care of the 40 kilograms. We have the 20 meters, and that's over here. We have the 30, sorry, and we have the 50 meters here, which means that if the whole wire is 50 meters, and if one side of the box where it's attached compared to the other side that's attached to the ceiling is 20 meters. We're going to subtract 50 by 20 to get the length of the wire on the other side. Now we want to figure out the tension force acting on the box in this direction, so we can call that tension 1, and the tension force acting in this direction, and we can call that tension 2. And yeah, let's get started. So to figure these tension forces out, this one and this one, we need to break them down into their x and y components. And to break them down into x and y components, we need an angle. So we need either this angle or this angle. And there isn't too many ways we can get to this, but we can, there are different ways of getting there, but I'm going to draw an imaginary line which is parallel to the ceiling. And then we can use Z pattern, this pattern over here, to say that this angle over here is the same as this angle over here. So I will write theta 1 for this one, and that's same as this. And we're going to use the Z pattern also here, and this angle is equal to this angle. So this theta 2 is equal to theta 2. To figure out our angles over here, these two, we have all of the three sides, so we can use the cosine law. And the cosine law states that the opposite side to angle, so I'm doing theta 1 first, the opposite side squared is equal to the other two sides squared, so 30 squared plus 20 squared minus 2 times 30 times 20 times cosine of my angle. I'm going to rearrange this, so I'm going to subtract both sides by these, so I'm going to get 32 squared minus 32 squared minus 20 squared is equal to negative 230 20 cosine theta 1. And 30 minus 30 is 0. We got negative 20 squared, which is negative 400, is equal to 2 times 30 is 60, times 20 becomes negative 1200 cosine of theta. We will then divide both sides by negative 1200 to cancel this, and we get cosine of theta is equal to 1/3, or theta 1 is equal to 70.5288. Now we can use the exact same idea to find this angle over here. We can do 20 squared is equal to 30 squared plus 30 squared minus 2 times 30 times 30 times cosine of theta 2. But basically looking at this, we can see that this side is 30 and this side is also 30. That means that this is an isosceles triangle, and this angle is equal to this angle. So that means that this angle over here is 70.5-ish, and this angle over here is 70.5-ish, and that means that this angle is equal to 180 minus 2 times 70.5. And I'm putting the exact values in, not the approximations, so theta 2 is equal to 180 minus 2 times 70.5288, and I will use the exact values from my calculator to get theta 2 as approximately 38.94244 degrees. Now that we've done the geometry part of this, we already have the angle, so we're going to redraw everything, and I'm going to use a force diagram. So for our force diagram, we have to look at what our box is interacting with. And this box over here, we're going to imagine that we have Earth down here. This is Earth, and our box is being pulled down by the Earth by force of gravity. And we'll calculate that force of gravity a little bit later. We're going to have tension 1 because our box is also interacting with a string here and a string here, so, or a wire, sorry, and this one over here is going to go in this direction. This is going to be my tension 1, and the angle here, actually I'm going to draw it a little bit bigger, much bigger, and I'm not drawing everything to scale. I do apologize for that. This angle over here is going to be theta 1, and we're going to have tension 2 acting at an angle in this direction, T2, and this is going to be theta 2. And force of gravity, I need to draw it a little bit bigger than this, just for, I know it's not to scale, but it's really out of position right now. So Fg here, and we got my 2 tension forces here. After drawing a free body diagram, we want to break down the forces into their x and y components. So for T1, we're going to have an x component in this direction and a y component in this direction. And we often want to, whenever we're breaking down the forces within our force diagram, we do want to use a dash mark and not a solid line, because if it was a solid line, that means there's an extra force going this way and an extra force going this way, but that's not the case. These are just two components of the tension force. So the x component of this, I'm actually going to use an x and y, positive x and y coordinate system over here as well. So the x component here, its magnitude is going to be T1 multiplied by cosine of theta 1, and that's because it's the adjacent side, so this is going to be T1 cosine theta 1, and the other side is opposite, so it's going to be T1 sine theta 1. For T2, the adjacent side is going to be T2 cosine theta 2, and the opposite side is going to be T2 sine theta 2. For FG, it only has one component, it doesn't have an X component, and the Y component is just going to be the magnitude of FG. Now, for the next step, I am going to write Fnet x and Fnet y equations. I'm going to take right to be positive, similar to what I did for my positive x coordinate system. Forces acting in the positive direction, so from T1, it's T1 cos theta 1, and that's acting in the right direction. That's same as my positive coordinate system, so I'm going to keep that as positive. Then the next force in the x direction is T2 cos theta 2. That's going in the opposite direction as my positive coordinate system. So that's going to be negative T2 cos theta 2. And that's going to be mass. That's going to equal to mass times acceleration. Since I know that my body here is not actually accelerating, the box is stationary, this acceleration is going to equal to 0, so mass times 0 is going to equal to 0, and I will get T1 cos theta 1 minus T2 cos theta 2 is equal to 0, meaning that T1 cos theta 1 is equal to T2 cos theta 2. And I'm going to put in my angles now because I can. So T1 cos my theta 1 is 70.5 approximately, and that's going to equal to T2 cosine of theta 2, which is approximately 38.9 degrees. So I'll put the degree sign as well. And this is going to be my first equation that I'm going to need a little bit later on. I'm also going to write the equation for the y direction. So for the y direction, I'm going to take up to be positive. F net y is going to equal to, I have this force going upwards in the same direction. It's going to be positive. This force is also in the same direction. It's going to be positive, and I'm talking about direction of my positive coordinate system. And FG is in the opposite direction as my positive coordinate system. So this one, I'm going to use a negative value. So I am going to have T1 sine theta 1 plus T2 sine theta 2 minus force of gravity is equal to mass times acceleration. It's not accelerating, it is at rest, so I'm just going to put 0 here. I'm going to add Fg to both sides, so I'm going to have T1 sine theta 1 plus T2 sine theta 2 is equal to Fg. Fg is same as mass times gravitational acceleration, so mg, and I'm going to plug in all my values. I'm going to have T1 times sine of approximately 70.5 plus T2 times sine of approximately 38.9, and that's going to equal to my mass, which is 40, times my gravitational acceleration, which is 9.81. This is going to be my second equation. Now, I have two equations. I'm going to write them down here. I'm going to have T1 cosine of 70.5, and I'm going to subtract both sides again by T2 cos 39, so it's going to be T2 cos 38.9 degrees, and that equals to 0. And that's my first equation. And for my second equation, I have T1 sine of 70.5 minus or plus T2 sine of 38.9 degrees, and that's equal to 40 times 9.81. I have a system of equations. I have two equations and I have two unknowns. Basically, I can rearrange here for T1 and then plug it back into this equation and solve it from there, or I can use elimination. Again, you can use substitution, elimination. I am going to use my calculator because it's a much easier method. So graphing display, I'll just write calculator. And I'm going to get a value of T1 and T2 as 324 approximately Newton and 139 Newton. And these are the values for the tension forces. And let's just say that the question asks for the magnitude of the tension. If you were asked for the direction, then you would include the fact that it's theta 1 degrees, so that's 70 degrees from the horizontal, and this one over here is 38 degrees from the horizontal. Okay, for our final question, we got Robo who's doing a pull-up. Robo's mass is 60 kilogram and has arm lengths of 1. Determine the tension in Robo's arms when the angle between the arms are at 60 degrees. So that's when Robo is doing narrow grip pull-ups, and 120 degrees, then that's when Robo is doing wide grip pull-ups. Let's try the situation out. We got, let's say this is a chin-up bar, and we got Robo. This is the arms for Robo, and in the first situation the angle here is 60 degrees. Length here is 1 and 1, and that's all we're given. And we want to figure out the tension in the arms. We know the mass of Robo. We're going to consider that Robo here is just a box, and it's got a mass of 60 kilograms. And in the second situation, I'll draw that over here. We got the angle between the arms is now 120 degrees, and we got arm length of 1 and 1, and we got the same mass. Mass is 60 kilograms. The first part of answering a question is always drawing it out, and we've done that, but we need some geometry. We need to figure out some angles here. We want to figure out this angle and possibly this angle. Luckily in this question, finding these angles is a lot easier, so we know that these two sides are both the same, so 1 and 1, so this is an isosceles triangle. This is 60 degrees, so all of the angles in a triangle make 180 degrees, so 180 minus 60 gives me 120. So these two will add up to 120, so each one should be half of that. So 120 divided by 2 will be 60 degrees, and these two angles are going to be 60. And since we know that if we were to draw an imaginary line here, this angle will also be 60 because it follows the Z pattern, and this angle, for the same reason, is going to be 60 degrees. For the other diagram, I'll use a different method of finding the angle. It's going to be very similar, but I'll draw a line which is parallel to the ceiling right away. I know the angle in between is 120, and I know that the arm lengths are both 1. So basically, if we know that this whole angle is 180, this angle over here is 120, so these two angles will add up to 180 minus 120, which is 60. Since this is an isosceles triangle, this angle and this angle is the same, meaning this angle and this angles are also the same. So the 60 is going to be divided into 2 sections. So we're going to have 30 degrees here and 30 degrees here. So I will write that down here. Okay, the next step is to draw a force diagram. I'm going to do this one over here, the left one over here. We're going to have a force of gravity. So that's going to be acting downwards. We're going to have a tension force coming from 1 going this way, and we're going to have the other tension force going this way. The angles are the same, and intuitively we know that those two tension forces are the same, but let's just imagine that we don't know that, and we're going to figure it out based on the calculations. So we got T1, we're going to have to break them down into its x and 1 components now. So this side over here is going to be T1 is adjacent to the angle, so T1 cos 60. And this one is opposite to the angle, so this one is T1 sine 60. Similarly, this side is going to be T2 cos 60 because it's adjacent, and this one over here is going to be T2 sine 60 because it is opposite. We will then write the net force equations in the x and y direction. I will choose right and up to be positive, so this is my x and this is y. So in the x direction, positive F net x is equal to the forces acting. This one over here is in the same direction as my coordinate system, and this one is in the opposite direction. So one is going to be positive and one is going to be negative. So we know that T1 cosine 60 minus T2 cosine 60 is going to equal to 0. And it's 0 because in this question we say that robot is hanging stationary, and that means the acceleration in the x direction is equal to 0. So absolutely no movement there. Because of this, we can just rearrange this and we will get T1 cosine of 60 is equal to T2 cosine of 60. And all I did there was to add T2 cos 60, and then I'm going to divide both sides by cos 60, cancel this out, divide this by cosine of 60, cancel these, and I will get that T1 is equal to T2, and that's my first equation. For the y direction, I'm going to do this, take up to be positive, and f net y is going to be, well, T1 sine 60 is going the same direction as my positive coordinate system. T2 sine 60 is also going in the same direction, and FG is going in the opposite direction. So we're going to have T1 sine 60 plus T2 sine 60 minus force of gravity is going to be mass times the acceleration in the y direction. It's not accelerating in the up or vertical direction, so it's going to be 0. So now that I have this, I know that T1 is equal to T2, so I'll just use T1 instead of T2 and plug that in here. So T1 sine 60 plus T1 sine 60 is equal to, and I'm going to add FG to both sides to get equals FG. Now we're going to have 2T1 sine 60 is equal to, and that's T1 60 plus T1, it's T1 times sine 60 plus T1 times sine 60 is equal to 2T1 sine 60. And on the right hand side, FG by definition is the mass times gravitational acceleration. We want to figure out the tension forces, so I am going to divide both sides here by 2 sine 60. And I'll put all the values in, so I will get T1 is equal to m, which is 60 times 9.81, and I'm going to divide that by 2 sine 60. Doing all this, I will get that T1 is approximately equal to 340 Newton. And I know that T2 is same as T1, that's up here, so T2 is going to also equal to approximately 340 newtons. For the other angle, I'm going to just draw a separator here. I'm going to draw the forces first. So we're going to have a force acting in this direction. That's going to be T1. It's going to have x components like this and y component like this. This angle is 30. This is going to be T1 cos 30, and this is going to be T1 sine 30. And we're going to have T2. T2 is going to have two components. This component is going to be T2 sine 30 because it's opposite to the angle, and adjacent side is going to be T2 cos 30. We're going to have a force of gravity acting downwards, so I'm going to write that as Fg. We're going to follow the exact same steps. We're going to take right to be positive, and we're going to write F net x is going to equal to, we have one force acting in this direction, that's positive because it's same as our positive coordinate system. This one is in the opposite direction, so that one is going to be negative. So we're going to have T1 cosine of 30 minus T2 cosine of 30, and that's equal to mass times acceleration. In this case, our object is stationary, as it says in the question, so it's going to have a 0 acceleration. So following up, we get T1 cos 30 is equal to T2 cos 30. We're going to divide both sides by cos 30 to get T1 is equal to T2, very similar to the last question. And this is going to be our equation 1. We're going to do the same thing for F net y. And this time the forces acting upwards are T1 sine 30 and T2 sine 30. And the force acting downwards is Fg. And that's going to equal to mass times acceleration. The object is not accelerating in the vertical direction, and therefore this is going to equal to 0. Okay, once we have this T1 sine 30, this T2 is same as T1, so I'm going to replace this with T1 as well. So T1 sine 30 plus T1 sine 30. I'm going to add Fg to both sides as I did in the last question to get Fg here. T1 sine 30 plus T1 sine 30, that's 2 times T1 sine 30, and that's equal to Fg, which by definition is mass times gravitational acceleration. I will divide both sides by 2 sine 30, and I will get T1 is equal to mg, mass is 60, and gravitational acceleration is 9.81, and I get 2 sine 30. Sine 30 is 1/2 times 2 is 1, and well, if I put everything on my calculator, I will end up getting 589 approximately, and that's rounded to 3 significant figures. And so T1 is equal to this, and T2 is going to be exactly the same based on equation 1 up here. And we can see that just being stationary and holding the bar using a narrow grip of 60 degrees, the tension in our arms is only going to be 340. Actually, this is if your arms are 1 meters long, but if we were to hold it using a wide grip, then the tension is going to be much higher. And we can see that even if our arms were longer or shorter, it didn't really matter. The tension is always going to be higher if you're just stationary and holding your arms in a wide grip as compared to the narrower grip. I know this was a very long video, but I hope that it was helpful in giving you some examples with some of the force type questions, and thank you for watching.